I would like to introduce our first speaker, Alex Sadeghi, who will be presenting Building Resilience, Meta-Scalable and Independent OOB Ecosystem. Alex is a network engineer at Meta and traveled from Brooklyn, New York to join us today. This is Alex's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Alex.
Oh, thank you. Appreciate it. Hey, what's going on? Thanks for the introduction, Michael. So I'm very excited to be here today. Thank you all for your time. Giving me the opportunity to come here and talk to you a little bit about out-of-band networks and how we can take them to the next level to have a resilient tool in our toolkit that can be used to recover and restore connectivity during catastrophic outages. This is a pretty loaded topic, so if you'd like to further the conversation, I'd love to connect over LinkedIn and keep the conversation going. Okay, so out-of-band management and disaster resiliency in general are topics that are easy to overlook. They're easy to fall to the bottom of your stack rank in terms of priorities. And it's just because, when things are working, you don't really notice them. But when things go wrong, that's when you realize just how critical they are. So my hope is that if you already have an out-of-band or disaster recovery strategy in place, today's talk will motivate you to perhaps look forward to how you can evolve it. And if you don't have one yet, you'll start considering why putting one in place makes sense. So this talk will be divided into three main sections. First, we'll start out with an out-of-band 101 and just kind of go over the fundamentals of management and console connectivity. Then we'll shift gears and examine some of the limitations of traditional conventional OOB designs, which typically stem from an over-reliance on peering with your production network in order to reach remote services like provisioning servers or your VPN. And then we'll share some of the approaches Meta has taken to mitigate these limitations and ultimately how we've evolved our OOB infrastructure to have it operate completely independent from our in-band network. All right, so let's get started. So first, what is OOB? So for the purpose of today's discussion, we'll be focusing on out-of-band as it relates only to network infrastructures, so your routers, switches, or optical transport systems. So OOB refers to any management or access path that exists outside your primary data plane. So today you'll hear me refer to your non-OOB path, your in-band network, as exactly that, in-band or the production network. And what I mean when I say that is just your primary data path. So the production network that carries real traffic, your user traffic, your server traffic, your application traffic. And this, this flows typically through your routers and switches. They're uplinks and downlinks, whether they be, 400 gig backbone links or 10 gig top of rack switch links. That's what I'm referring to when I say in-band or production. On the other hand, out-of-band means a completely separate parallel network built for management, monitoring, and troubleshooting. And it's very important to make the distinction that this network is not meant to be a backup for your in-band traffic. So never should your user traffic fail over to the out-of-band network. But it's really there just for accessing, diagnosing, gathering telemetry, provisioning your in-band network. So access to this out-of-band network happens through two dedicated interfaces on your network devices, the management and console ports. And these in turn then connect to high-density console servers or management switches, which form the access layer of your OOB infrastructure. So although this isn't typical in the industry and won't be the focus of today's presentation, at Meta we've actually begun to deploy passive optical ONUs as part of our OOB access layer. My colleague MJ gave a great talk about this at the last NANOG, which I encourage you all to go check out. But again, for today's conversation, you can just kind of assume a standard out-of-band access layer of 48 port management switches and console servers. Okay, so why out-of-band? So as network operators, you know the enormous investment in time, money, and rack space that goes into maintaining your in-band network, right? So to then go put a similar investment in out-of-band is a big ask. And there, we'd expect there'd be some great trade-offs for it. And the three we're going to talk about today are initial provisioning, remote access, and full recovery. Before we explore those benefits, though, let's quickly differentiate what the difference between console and management access are, as they sometimes tend to get confused. So the management port is an Ethernet interface, which means it relies on IP connectivity. and therefore it can carry network traffic. Things like SSH, file transfers, SNMP and GNMI monitoring, and provisioning traffic. However, because it depends on the IP stack, it's only usable once your device has booted and has established network connectivity. So for times where that's not the case, that's where the console port comes in. It operates over serial communication independent of IP and therefore remains available even when the device is unconfigured, booting, or in a failure state. This makes it invaluable for low-level troubleshooting. And, however, because it does not run Ethernet, you can't pass network traffic through it. So to summarize, the console port is your most reliable, always available access method, ideal for recovery and troubleshooting. The management port is your network-based access method. All right, so we'll start off talking about provisioning. So the first major advantage of having an out-of-band network is during new site provisioning. And this can be a brand new data center or just an extension to your existing campus. So when a data center is first being commissioned, you have a bunch of devices you want to bring online. And building out a segment of your out-of-band network can help accelerate this build time. You can then use that pre-provisioned management path to build out your in-band network in a touchless manner. And at Meta, this was our initial primary motivation for deploying out-of-band infrastructure. During the construction phase, we don't yet have access to Meta's fiber optical backbone, so we need a first-in device that has no physical dependency on Meta's transport. That device for us is an out-of-band firewall, which is shown here in the diagram. It's connected via a direct internet link, which allows us to reach Meta's backbone and remote services like DHCP and provisioning servers. Because the internet link is a shared medium, security is critical for us, so we make sure to use IPsec-capable devices at both ends and encrypt the traffic, and then apply strict ACLs at the boundary between our out-of-band and production network to ensure that only pre-approved flows can cross that boundary. So once that secure OOB headend is online in the new data center, we can then begin to build out our out-of-band access layer, the management switches and console servers that connect to every device. So as a simple example for the rest of this section, let's consider a scenario where we want to build out a row of 120 routers and switches. So a common deployment pattern could be to just put a couple management and console switches at the end of each row. In this case, we can serve those 120 devices with just 3 48-port management switches and 3 48-port console servers. By provisioning those 6 devices, we are now ready to provision the rest of the row in a plug-and-play manner. So once they're up, you just have the techs or your infrastructure team run the cabling to the new devices, and ZTP or zero-touch provisioning can take care of the rest. ZTP lets newly powered devices automatically obtain their configuration and software images over the out-of-band network. Additionally, now that you have your out-of-band devices stood up, they're not only useful for the provisioning process, but you can depend on them later when your network's in a steady state if you need to do things like troubleshoot or restore configs to the network. Let's quickly zoom in on ZTP and go over how it works. So when a ZTP-capable switch or router boots up, it sends DHCP requests out its management interface that includes special DHCP options identifying its vendor, model, or serial number. And assuming your OOB network is properly configured with DHCP forwarding and routing, these requests will eventually reach a central ZTP server. This server then uses that identity data to determine which configuration file or OS image to return back to the device in its DHCP reply. Then your device that initially sent out the request downloads its configuration image and applies it and joins the network automatically. So in our example, this would allow us to parallelize the bring up of the entire row, the 120 devices, at the same time. If any device fails to boot correctly, let's say for some reason it's not sending ZTP requests, you then have your console network to dig in and see what's going on. All right, now let's move on to remote access. So as I previously mentioned, now that you have this out-of-band network in place, it's there for you when the data center is live and operating. If a device suddenly loses reachability to the production network, whether it's from a physical failure like a bad optic, a faulty fiber, or a power loss, or from a logical error like a bad configuration push, your OOB network gives you a lifeline. Through the console and management connections, you can remotely access the device, you can diagnose and isolate the fault, and you can, in many cases, roll back or correct a bad configuration. All this happens without needing to dispatch a tech or smart hand support on site, which saves time money, and operational downtime. Now, up to this point, we've looked at out-of-band networks that ultimately peer back to the enterprise backbone to reach remote resources like DHCP or VPN endpoints, and that's a very common out-of-band design pattern. However, this interconnection means that the out-of-band and production networks can share fates. So that means that if something catastrophic happens to your in-band network, it can result in your out-of-band network being down at the time when you need it the most to recover that fault. So in the next few slides, we'll explore a few corner case disaster scenarios where this shared dependency can limit the effectiveness of your out-of-band network. So in this example, let's imagine a topology where our VPN resides on the production backbone, which is normally how engineers would then reach the out-of-band devices. Suppose a large-scale configuration error occurs. So let's say that maybe to take a device in your backbone offline, typically you just import/export nothing via BGP, right? And that's common. That's a common tool in your toolkit they use just to take one device offline. But maybe you have a flaw in your push system and you accidentally push that to all routers. Now this might sound extreme, but the same principle can apply to smaller scale issues. So maybe you just take one data center offline, but the point is that you isolate a segment of your network. So in this extreme scenario, your outage doesn't just take down your backbone, but it also takes down your out-of-band network as it was dependent on that backbone, and it also takes down your corporate VPN as it also was dependent on the same backbone. In this case, you've gone completely dark and you've lost remote visibility and control. You've also lost your ability to connect via console and investigate and restore connectivity, the exact situation OOB was meant to avoid. And you're most likely needing to dispatch people to the sites to physically console in. And also you may not even know where the issue lies, right? Because you've completely gone dark. So in this scenario, you're completely isolated and you're looking at hours until you restore the outage. So if there's one thing I want everyone to take away from this presentation, it's to regularly challenge yourself and think about what can go wrong in your network and how you would recover from it. As network operators, uptime is our job, and it can be a thankless job most of the time, right? When the network is up and running, customers are rarely going to reach out and say, thank you, you're doing an amazing job. But when it goes down, everyone's going to notice. I'm sure many of us can remember a moment, maybe even recently, when a network issue left us completely locked out with no visibility into what was happening. The BGP example we just discussed might sound extreme, but it's not purely theoretical. In fact, Meta experienced a very similar large-scale outage, one we refer to as access denied, and that's what directly inspired many of the architectural enhancements we'll cover next. So with that in mind, let's dive into how we've made an OOB ecosystem that is completely independent from the production network possible at Meta. So the first step in ensuring our true out-of-band resiliency was giving our corporate VPN direct access to the out-of-band network. And the way we did this at Meta is by deploying a secondary VPN, which we call the OOB VPN. One key practice we recommend is to use the same VPN client for both the corporate and out-of-band VPN, just to keep the user experience identical and to prevent confusion when engineers need to switch to the out-of-band VPN during an outage. Like most things, we'll kind of cover in this section, there is flexibility, right? You may choose to host these services on-prem, such as your out-of-band VPN, but actually in this diagram, I've illustrated that the out-of-band VPN is terminating in the cloud at AWS. So you have that flexibility, but what matters is that the VPN peers directly into your out-of-band network. So you want it to have no dependencies on the production backbone, as we're assuming that may not always be up, right? So what we've done at Meta is we've deployed Cisco Firepower firewalls, which serve as the gateway for AnyConnect VPN client, the same client we use for in-band VPN, and that firewall peers directly with our out-of-band network in 8 of our data centers. I'm pointing out 8, and the reason for that is that we don't just have 8 data centers, we actually have hundreds. But the reason it's important to note that we're only deploying in 8 is because we want to be able to then VPN in that firewall and reach any out-of-band network we need to, right? But in order to do that, we'd need to deploy 100 or as many data centers as we have, VPN terminating gateways, right? Which is something obviously that does not scale well. And it would also leave you in a disaster scenario needing to know exactly which gateway to point to. So that kind of begs the question, how do you get from site to site? And the answer is you need to build some sort of independent site-to-site transport. So the way we've done this at Meta is we've built a completely independent out-of-band backbone. And this connects the OOB layers from every data center and POP site. Now, this might sound a little daunting. We all know that backbones are one of the more complex parts of the networks we run. However, it's important to keep in mind that you only need to build out this backbone out to the complexity of the traffic you're trying to carry. So, the use cases we're talking about today are kind of about just carrying low volumes of control plane monitoring traffic, right? So at Meta, the way we've accomplished this is by creating a partial mesh of core routers, which we've geographically located in every continent where we have data centers. We've then interconnected these routers and the connections into our POPs and data centers with 10 gig lease carrier circuits with no traffic engineering. So it's a relatively simple backbone, and that kind of goes to show that this doesn't need to be some crazy complicated backbone. The important thing is to just make sure you have site-to-site connectivity between all your different endpoints. Okay, so now we have an out-of-band VPN and an out-of-band backbone in place. We can now reach any console or management port of any device remotely from the comfort of our homes. But remember, most of our critical network services, things like your monitoring stacks, DNS, DHCP, they normally live on servers in the in-band network. So in the examples we're talking about, if that network fails, those services and tools go down too. So to maintain visibility and recovery capabilities during major outages, it's best to host a Minical server infrastructure directly inside your out-of-band network. So at Meta, we're very reliant on very pretty and nice graphs, right, that visually display the information in our data stores and our collections traffic. So one of the things we made sure is that, we kind of pulled our network operators and asked, hey, what are the minimal sets of graphs and tools you need to do your job in a disaster? And we've made sure we host those in our out-of-band server stack. That, as well as things like DNS, DHCP, and important config, the last well-known config backup of every network device, as well as the OS images they boot up with. Just like our out-of-band VPN, you don't need the server stack everywhere, right? Because you have the out-of-band backbone, you really only need the server stack in a couple sites, and then you can rely on your site-to-site transport to get that data wherever you need it. All right, so now let's revisit our catastrophic failure and kind of go through how this ecosystem we've built out could help us recover from it. So again, we're at the point where we push out this really bad BGP config everywhere, right? We've gone dark. The fire alarm's gone off and you're asked to recover the network. The first thing you're going to do is authenticate to your out-of-band VPN. And that's, again, this should be the same client that you use for your day-to-day job. You're just pointing it to a different gateway. So the first thing you want to do is use your high-level troubleshooting tools, right? The ones you've stored on your server to do your grouping of bandwidth. Maybe you visually display all the recent network changes. And this can help you kind of pinpoint where in the network the issue might be. You can then move on to your more low-level troubleshooting. So, maybe you kind of have a good idea of a set of devices or one device where the issue lies. Let's get into that console management interface and run some commands there to just verify exactly where the issue came from. Once you know where the issue is, it's time to restore the network. So this can be as simple as doing a rollback on one device, or in the example we're talking about where we've pushed a bad config to many devices, you can log on your out-of-band server and push the last good known config of each device to all those devices over your out-of-band backbone. And I know that's a very simplified, high-level example, but that's very in line with what we do at Meta to diagnose and restore these kind of large outages. And we've seen it take our time to recovery down from hours to minutes in many instances. So now let's talk about some considerations that I'd like to leave you with before we wrap up the talk here. So first and foremost, it's very important to sit down and define what you're trying to optimize for. All of our networks are different. And we may have different customer SLAs that you should be building out your solutions for. Perhaps for you, having a network that's up 100% of the time isn't necessary, so maybe some of what we've talked about today is overkill. In any case, I think we could all benefit from at least the minimal set of benefits that this provides. So it's important to kind of make sure you're building out for what will help you out. You also want to make sure you have space for your, this out-of-band network. It's not free, so it's going to take up rack space. You're going to need to figure out how many ports you need. So all those calculations are important. Then you're going to want to figure out if you want to build this completely on site in your data centers or in your campuses, or if you want to outsource some of this. For us at Meta, personally, it's very important to have the control. We don't like to be dependent on carrier uptime. We like to control our own fate and also plug in our own systems into our automation systems. So that's why we choose to put things on-prem when we can. But for you, that may not make sense. Also, be sure to start small. These networks, again, it's another network, another piece of infrastructure you have to manage. So you want to make sure you have the proper team staffing. And if not, you want to start slow and not overwhelm your team. These next 2 points are two of the most important points I'd like to leave you with. The first is to perform regular doomsday thought exercises. So I hope if there's one thing you can take from this, it's that you all go back to your teams and you sit down and kind of think through what are the worst things that can happen in our network. And be realistic. Obviously, the worst thing that could happen is all your data centers blow up, right? But let's be realistic. Try to sit down and think through how you run your network and what some of the things that could go wrong given the way you push configs out day to day could be. And then ask yourself, how would you recover from it? Are there any gaps? Is there anything you can learn from or build out to mitigate these gaps? Once you're in a place where you feel like you have a sufficient infrastructure to recover and address some of these gaps, run regular drills. Do not assume that when something goes wrong, you're going to automatically be able to recover and you're going to know how to use your tools and everything's going to work just fine. You need to regularly drill and stress test your infrastructure, right? It's a muscle that you need to be working out. At Meta, we do this at least once a month, where we require any engineer with access to the network to run a drill and demonstrate that they know how to operate these tools so that when the time comes, they can get online immediately and start restoring the network. Finally, do you have, so it can also be really easy to go down a rabbit hole of like endless scenarios that you need to recover from, right? So, it's easy to, I guess, envision like, hey, how would we recover from a big in-band failure, right? But then maybe you get into the thought pattern of, okay, what if my in-band network is down and my out-of-band network is down? Then what do I do? Well, then maybe you have, a cloud link to restore your out-of-band network. But then what if the cloud's also down, right? So the point I'm trying to make here is there's always going to be a scenario you can conjure in your mind that you have to recover from. But the point is to be realistic and try to cover for the most probable scenarios of disaster and downtime and make sure you cover those bases. So thank you all for being here. I hope you learned a thing or two. And yeah, I guess it's time for questions.
Hi, my name is Darcy with Acronis International. We've done an awful lot of what you're talking about, but we've went with a distributed model for the ZTP done on the serial devices, etc. Is there, had you considered and weighed out the options for doing the centralized ZTP, DHCP, etc., and having DIA links versus having the lower cost like LTE and distributed Docker containers doing ZTP locally?
Yeah, so the conversation, I don't think we've considered it for this exact scenario, but definitely the topic of like whether we kind of do things in-house or go to the cloud is one we have often. And at some points it does make sense to go in the cloud. However, we've just in terms of pulling into our automation systems and writing code that is very adaptable to the devices we control, we typically opt to have things in-house and centralized. Thanks for the question, Darcy.
Any more questions in the audience or any remote? Okay. Seems like no more questions, so thanks, Alex, for a great talk.
All right, thank you all.